Okay, 7.2 is about linear programming. What your main goal is you have some constraints and you want to maximize or minimize something given those constraints and to find out the maximum or minimum product you can produce. So what we have is first a feasible region. A feasible region is either you're going to be given to it or you're going to be given the equations to graph it. It's basically the common ground between all the functions you're graphing, like areas the above or below, just reduced to like a single shape sometimes. And it's any set of coordinates inside the feasible region are the things you can plug in to the thing you're trying to maximize or minimize in order to find where your best data point is. The maximums and minimums of the objective function will always occur at the corners or endpoints of the feasible region, so you don't need to test every value in there, you just need to test corners that you can see. Now some corners, if it's a minimize, will go on forever, so just keep that in mind. You don't need to plug in any large numbers. If it looks like it goes on forever, there won't be a corner up at that area. The objective function is the thing you're trying to maximize or minimize. So sometimes you'll get constraints for the graphing, and sometimes it'll say maximize or minimize this function. So given the following feasible region, which is graphed below, find the maximum value z can take if z is the function 3x plus 4y. So if we look at these four corners, the 4 points we've got are 1, 8. We have -1, -2. We've got 9, 7. And we have 9, 1. So all I have to do is plug these points into my formula. Z equals 3 times 1 plus 4 times 8. It's 3 plus 32, which is 35. So that means the product there is 35 if we plug in the first point up here into the function. The second point, 3 times -1 plus 4 times -2. That's -3 plus -8, which is -11. How we should normally write this, though, is you can get used to writing it z of 9, 7 if you want. It's really kind of a function of x and y. You can write f of x, y. It doesn't bother me if you just plug it in. You just need to know which point is which. 3 times 9 plus 4 times 7 is 27 plus 28, which is 55. And 9, 1 is 3 times 9 plus 4 times 1, which is 27 plus 4, or 31. So the maximum value for z is the highest output that you saw. So 35, -11, 55, 31 is 55, and it's at 9, 7, the point. So that's the idea here. Now, it was already graphed for you, so sometimes you'll have to graph it yourself in order to find this, but that is the idea behind what's happening here. So let's continue with one that we'll have to graph ourselves. Maximize z equals x minus 6y given the following constraints. X is greater than 0, y is greater than 0, and 5x plus 7y is less than or equal to 35. Okay, so we know, we'll graph these two lines. We know that x and y being greater than 0 restricts us to the first quadrant. Now it says 5x plus 7y is less than or equal to 35. 7y is less than or equal to -5x plus 35. Divide by 7. We get y is less than or equal to -5/7x plus 5. So we start at the 5. We go down 5 over 7. This gives us this other line. And here, we've got our shape. Our feasible region is in the first quadrant, but below this line, which is here, the triangle. So what are my corners of the triangle? We've got 0, 5, 0, 0, and we've got 7, 0. So those are the three things that I will end up plugging in to see if I can maximize z. So at 0, 0, z is equal to 0 minus 6 times 0, which is 0. At 0, 5, we have z is equal to 0 minus 6 times 5. That's 0 minus 30, so negative 30. And lastly, at 7, 0, we've got 0, or z equals 7 minus 6 times 0. 7 minus 0 is 7. So we're trying to maximize. So we can say we have a max of 7 at the point 7, 0. And that's really how this works conceptually. Now, it was an easy triangle to draw. Sometimes your equations are a little bit more complicated. So let's see what happens on this last problem. Find the maximum and minimum, so for max and min, of z equals x plus 5y, given the following constraints. We have x plus y is less than or equal to 10. So I'm going to write this over here as y is less than or equal to negative x plus 10, so that I can graph it. Start at 10. Slope of negative 1 will go like this. Negative x plus y is less than or equal to 2. This is y is less than or equal to x plus 2. So start at 2, we have a positive slope. And lastly, 2x minus y is less than or equal to 5. So negative y is less than or equal to negative 2x plus 5. When I divide by a negative, I get y is greater than or equal to 2x minus 5. So I'm going to start at 5, or negative 5, and go up by a slope of 2. Okay, so we drew a picture. Now, where are we supposed to be? We're supposed to be greater than this last line, the 2x minus 5, but we need to be less than the other two lines. So if we shade the area that is less than these two lines, the negative x plus 10 and the x plus 2, but greater than the other line, we'll get this infinite area. So what I want to do is, let's change the equation for one of these, and I'd like it to be this triangle. It would make the most sense to plug in for. We'll change so to get this triangle, I need it to be above the negative x line. So we'll change it to greater than this, which is greater than, for the convenience of our problem. And that would create the shaded area for all of these in here. Now, if I look at all the corners here, it looks like we have the 0.46, the 0.55, and the last point on the top right is 7, 9. And if we plug those all in for z, we get z equals 8 times 4 plus 5 times 6. 32 plus 30 is 62. Z equals 8 times 5 plus 5 times 5. It's 40 plus 25 is 65. And z equals 8 times 7 plus 5 times 9. This is 56 plus 45, which is 101. So if we're trying to find the max and min, we have a max of 101 at 7, 9, and a min of 62 at 4, 6.